Okay, so
Again, nuclear reaction, is that just a reaction
okay.
that occurs in the nucleus?
Okay, so a nuclear reaction. So the key to a nuclear changes is different than everything else we did this semester. Everything else we did, or this year, everything else followed the law of conservation of mass. Everything else followed the law of conservation of energy. Nuclear changes break those rules. Okay, so it's going to put the yearbooks away. They just distract you. Okay, so the nuclear stuff is where the nucleus changes. It either falls apart or comes together, and when you do that, you make entirely new atoms, which is different than what in a chemical reaction, we don't make new atoms, we just rearrange the ones we have. Nuclear is different in that it makes new kinds of atoms, changes one element into another. Okay? So the nucleus changes. So you're going to change one kind of atom into another, and there are several kinds of changes it could do. There's alpha decay, beta decay, and gamma fission, and fusion. Okay. And alpha decay is the alpha particles from Rutherford's experiment. It's a helium nucleus. Remember, the number on top is protons plus neutrons. The number on the bottom is just protons. So because this is number 2, it's helium, because all helium has 2 protons. This is a special isotope of helium, helium-4. It's the most common one. But helium-4, that means that it's got 2 protons and 2 neutrons. Okay? And this piece comes flying out of the nucleus. So when you write that equation, like this is the one kind of thing that happened in the Bell work today. You had 236, 92 uranium. And I said you made an alpha particle. Okay? Nuclear equations are balanced in a different way. It's a much easier way. The numbers have to add up. Okay? So the top number is 236 on the reactant side. On the product side, it's got to be 236. So to be 236, it's got to be 232, whatever it is. That's going to make the top 236. And the bottom's got to be 90. And number 90 is thorium. So nuclear equations are easier to work and balance than chemical equations. But the difference is I make an entirely different kind of atom. Okay? So a nuclear change will always make an entirely different kind of atom. Okay? Beta decay is an electron coming out of the nucleus. And symbol is E for electron, 0. We put a -1 down there, not because its charge is -1. That would be on top. Put a -1 down there because that's what it's going to do to the atomic number. Okay. So if I have something that goes through beta decay, say, this is the most common one that does it, carbon-14. If it goes through beta decay, I can either write it as a beta or as an electron, either one's okay. If I can just write a beta. Okay. What is the other piece going to be? Well, the numbers have to work out. The top number's got to be 14, because 0 plus what gets me 14? 14. And the bottom, in order for that to work out, what plus -1 gives me 6? 5 plus -1 gives me 6? 7 plus -1 gives me 6. right? See how this number, the bottom adds up to 6 still? And so the symbol for element number 7 is nitrogen. Now, there's I put this was it. I forgot there's another one here we had with positron. Positron decay. And a positron is just the same mass as an electron, but the opposite sign. Okay? And so a positron has that symbol. It's antimatter. We never see positrons because as soon as they run into anything else, they annihilate it. Okay? But we can change the nucleus, but as long as we know that a positron just has that opposite sign, then sorry, 1680. If oxygen went through positron decay, it would make 16 and 7 nitrogen. So, and gamma doesn't have a mass number or an atomic number because it's just high energy light. No, it doesn't change it's just a way of getting rid of energy. And just a way of getting rid of energy.
So gamma was wasn't like the one that is like bad for you?
Well, but gamma is light, so because it has no mass, it can penetrate everything.
And then it just like, I think, what was it? Not lead, it was...
Yeah, they usually put feet of concrete. We'll talk about that penetrating power in a little bit. Okay. So I want to talk a little bit about how do we know what about. I'll talk about fission and fusion a little bit. Alpha, beta, and gamma. Okay. Penetrating, what they can go through. Alpha decay is stopped by paper. Okay. So alpha decay is alpha particles are only dangerous on the outside of your body or if you inhale them in your lungs. What? You can inhale, what happens is in the Midwest you inhale radon. And radon goes through alpha decay. So while it's in your body, it's giving off those alpha particles. Okay. Anybody watching the Chernobyl series? I'll show you.
We watched it at school something about it.
No, actually, there's HBO is playing a new series about what it was like to be in the plant at Chernobyl when everything was going wrong. And the alpha decay, what happens is if you get it inside you, it's going to kill you from the inside out. So all the firefighters there that were breathing that stuff were getting cooked from the inside. We're getting cancer on the inside because they were breathing the stuff in. Beta will go through paper, and it's stopped by aluminum. Now, oftentimes they say aluminum foil, but I tried aluminum foil. You've got to put several pieces before it gets stopped. It's got to be a fairly thick piece of aluminum. Aluminum foil by itself is not quite enough, but aluminum will stop it. Okay? Which means that it's dangerous. It can go into your body. So it causes cancers inside your bones, inside your organs, because they can penetrate from the outside in. And gamma is stopped by lead or feet of concrete.
Isn't that why they put like around the thing that exploded the
Yep, that's what
like concrete thing?
they put a concrete tomb around it to try to stop some of that from coming out. And actually, they, in the last year, just completed a building that covered the whole plant. World's largest movable building. They built it next to the plant and built rails and rolled a building across the top of it to seal it off. Because the concrete was starting to fail because that radiation destroys concrete too. It changes. So when it hits that nucleus, it can change that nucleus into a different kind of nucleus. And if it's not calcium, then it's not concrete anymore. And the concrete starts to crumble. One of the interesting things they showed on that TV series was an actual live picture of a helicopter that flew right over the reactor core that was exposed. And it fell apart in pieces after sitting there for a minute. Because the radiation hits the metal stops being metal. Or it turns into a different kind of metal, which isn't as strong. The helicopter fell out of the sky. And so one way we can detect it is by how fast it goes through. The other way we can detect it is by what happens to it with charges. So if I shoot particles and I put a positive charge here and a negative charge there and detect where they come out, there'll be 3 different places. There'll be one right down the middle that isn't affected because it doesn't have a charge. And that's gamma. It doesn't have a charge, so it won't be affected by the positive or negative charge. The alpha particle is a helium nucleus. That means it's got 2 positive pieces, 2 neutral pieces, so it's positive. So when you shoot an alpha particle, it's going to turn towards the negative sign. It's going to be pulled towards the negative sign, so alpha is pulled towards the negative. And beta is an electron, so it's going to be pulled up, and it's going to be pulled up a lot more because an electron weighs a lot less than a helium nucleus, so it's easier to turn. Just like turning a truck is harder than turning a car, same kind of thing. So that's how we can detect those 3, alpha, beta, and gamma. Then we have the other 2. Fission is a large atom turning into 2 smaller atoms. Fission is what we use in nuclear power plants. Fission's how we make atomic bombs, the ones we dropped on Hiroshima and Nagasaki, the ones we're worried about Iran and North Korea building. Okay, so if I have uranium-235, one of the things they kept asking on that Chernobyl show was, do you have any iodine tablets? Because one of the things you get out of that is iodine-127, which is radioactive. And when you breathe it, it gets concentrated into your thyroid and causes your thyroid to stop working. So when there's a nuclear reaction like this, they tell people to eat iodine so that you got lots of iodine in your system so the new stuff doesn't come in, so it can't build up so the radioactive stuff can't get there. Because there's radioactive versions of iodine and non-radioactive versions. We want the non-radioactive version in us. Okay? But what else would I make? 108, right? 108 and 127 makes 235. And 53 from 92 would be 39. Because 40 would be 93, so 39.
It would be
And and 39 is yttrium. Yeah. So the equations work the same no matter what it is. The tricky part is, if I tell you beta decay, you're going to have to write that 0, -1 on the other side by yourself. That's, once you get that there, then it's easy to finish it. You just got to remember what those pieces are. And so they use this. This gives us a lot of power because you destroy a lot of mass when this happens. Okay, but not nearly as much as fusion. And fusion is small atoms joining to make a heavier atom. Now, we're limited by what we can do is because in order to get those nucleuses together, you've got to overcome the fact that they've got those great big positive charges. And try to get those nucleuses to run into each other is tough. So it takes a lot of heat. Okay? So, but the only place it's hot enough to do it is places like the sun. That's what powers the sun. They're working on fusion power here on Earth. When I was in high school, they said it was 30 years away. I just read some new articles, and they say it's about 20 years away, so they shortened it. They've gotten to the break-even point where they can get more energy out of fusion than they put in to start it. They got to find a way to make it sustainable. Okay, so the hydrogen bomb is both. It uses a fission bomb to squeeze hydrogen together to make fusion happen. So it needs the fusion part isn't the dangerous part. The reason why hydrogen, all the radioactivity comes from the fact that you need a regular atom bomb to set off a hydrogen bomb. That's the challenge. So all the radiation comes from the atomic bomb, because fusion, while it's happening, gives off some neutrons, pretty high neutrons, but that's the only radioactivity. It's radioactivity free. Okay, so it's a lot safer if you can get to the 10 million degrees that you need to make it happen. And they're getting so they can manage those things a little bit better. But here's what fusion looks like as an equation. It's going to be different because it's going to have two things on this side. So four and two helium. And lots of energy. The problem is we talked about the idea of activation energy. The activation energy for these, the idea of activation energy would be that you have to hit them together as hard as they would be hitting at 1 million degrees and really huge pressures. And that's hard to do. And actually, all the elements heavier than hydrogen were made this way. Okay? And in a star, you take those heliums and run them into other atoms and make helium runs into a hydrogen, makes a lithium. You keep running into things, but in a star, the heaviest one you can make this way is iron. A star can be hot enough to make iron, but nothing heavier. So when it's making iron, it's giving off energy, but when it stops making iron, it cools off, and the sun starts to collapse on itself, which heats it back up, but it can't do anything with that heat until it collapses, and then explodes. And when it explodes, in that explosion, it can make everything heavier than iron. So all the elements that occur heavier than iron came out of supernovas. So since we've got some of these pieces in us, we're all made of stardust. We're made of the remains of stars exploding. So I think that's about what I've got for nuclear off the top of my head. Yeah.
I have another question for here. Can we go through again what the hydrogen calories to joule?
Calories to joules. Oh, calories to
And
joule.
like the big C and the
Okay.
little C calorie.
Little c calorie is 4.18 joules.
And what's with the big calorie?
One big C calorie is 1,000 small C calories,
Okay.
which is 1 kilocalorie with a small c. Because we don't want to say that we eat 2 million calories. We're only supposed to eat 2 million calories a day. Because it is 2 million little c calories, but we don't like that number because it's hard to go on a diet. Ooh, I'm only eating 1.8 million calories. That doesn't sound like much of a diet.
So here at number 1, how many kilojoules of energy are in a donut that contains 200 calories? So here we have to go then from big calories to small calories, and then from small calories to joules,
Joules.
and then from joules to kilojoules.
Yep.
Oh, wow. Okay.
Okay, so that's the idea. Okay, any other questions? Anything else come to mind about what you want reviewed? Okay. Well, you got some heat stuff to play with. I passed out some papers when we got here. So we got some heat work to do.